so let me go through this real quick. Okay, so we have a system of interest here. We have two cars, okay, and we have the momentum of one of the first vehicle. Okay, so we're going to call that P1. Then we have the momentum of the second vehicle. We're going to call that P2. Okay, and they're traveling along. Okay, and if I want to know of the entire system of interest, what our total momentum is, I would just add the two together, right? Like this says here. My dog is barking at me. She's not happy. Okay, anyway, so that is going to be my system of interest. Okay, now after, for this case, if they collide or something like that, we have a change in velocity, okay? Now, this change in velocity makes them have different momentums, so we can call that P1 prime and P2 prime. And again, our total momentum should be these two added together, okay? And that would give us some total momentum here. Okay, so this total momentum will be the same as the total momentum that we calculated before. Okay, so again, this is exactly what I'm saying here. Okay, so this is the idea of conservation of momentum. Okay, so once these vehicles hit, they will kind of exchange certain amounts of momentum and such, and their total momentum will remain the same. Okay, that is a constant value. Now, one thing to note here is that this is an isolated system, okay? And that just means that the net force overall is equal to 0. Okay, so there's no external force. Or there could be external forces, but the net of them, or the sum of them, should be equal to 0. Okay, so give me just a moment, and I'll be right back. All right, sorry about that. Okay, so let's go ahead and move on from conservation of momentum to a collision. So this is going to be our first type of collision. It's called an elastic collision. Okay, and we're going to look at that in one dimension here. Now, an elastic collision is defined as a collision that conserves internal kinetic energy. Okay, and so basically the sum of kinetic energies the internal kinetic energy is going to be the sum of kinetic energies of the objects in the system. Okay, so let's say that we have two blocks like we have here with mass M1 and mass M2, and they are sliding along a frictional surface. Okay, and so before our collision, we have two different momentums, okay, a P1 and a P2, and our total momentum, P tot, would be the addition of the two momentums. We learned that from the last one. Okay, so from conservation of linear momentum, okay, this is going to be the same as the total potential energy after the collision. Okay, so these two should be equal, first of all. Okay, and now in this elastic collision, the kinetic energy, the total kinetic energy, should also be conserved here. Okay, so my kinetic energy total for the before the collision is going to be kinetic energy of the first block plus the kinetic energy of the second block. Okay, now after our kinetic energy total, you can say prime, is going to be K1 prime plus K2. Excuse me. Oh, sorry. Allergies. Okay, K2 prime. Okay. And again, through this conservation, or because they are elastic collisions, these should be equal. Okay. So our kinetic energy should remain constant throughout. Okay. So let me take a quick pause here. My dog, I think she might need to go out, so I'll be right back. Okay, so we just discussed elastic collisions. Now let me go ahead and talk to you about the other type of collision, which is going to be inelastic collisions. Okay, so again, we're going to look at this in one dimension. Okay, now we have two blocks yet again. Okay, but this time we have that they are the same mass. Okay, so these two blocks have the same mass and they are moving towards each other. Okay, and in a perfectly inelastic collision, when these two objects are moving towards each other and when they hit, the objects will stick together. Okay, so this is a perfectly inelastic collision. Okay, and in an inelastic collision, the internal kinetic energy is not conserved. Okay, and it changes. So in the last one, we saw that the kinetic energy is conserved in an elastic collision, okay? But this time in an inelastic collision, the kinetic energy changes, okay? So again, in this perfectly inelastic collision, we see that we have some kinetic energy total before, and then after we have some kinetic energy after, okay? And in the perfectly inelastic, they will stick together, okay? Which means that there is going to be no motion, okay? So remember that kinetic energy is calculated as 1/2 mv squared, okay? And if the two objects stick together and their velocity goes to 0, okay, that means my kinetic energy is also 0, okay? So again, in this perfectly inelastic collision, my kinetic energy changes from being just the sum of these two kinetic energies to 0 because there is no more motion. Okay, remember that if there's no motion, there's no kinetic energy. Okay. Let me quickly explain a bit more. So again, in our before the collision here in A, we have that our P1 plus P2 is going to be our total momentum, right? Same thing with after the collision, P1 plus P2 prime is going to equals P tot. Okay, and from our understanding of conservation of momentum, okay, these should equal each other. Now, in this case over here, we know that our velocity went to 0, right? Okay, so that means that our total momentum here is going to have to be 0 since our velocity of both of these blocks are now 0. Okay, so this now translates to, in our before system here, okay, our before scenario, that our addition of momentums should also be 0. Okay, so watch out for that. This is all in your textbook as well, okay? So just wanted to kind of help you to understand what these mean, because this kind of comes out of nowhere, right? So we want to be able to understand where these equations come from. Okay. So one other thing to notice about, other than the kinetic energies are different, but why this kinetic energy is just mv squared, because I just said that kinetic energy equals 1/2 mv squared. Okay, so in this case we have the kinetic energy of the first one, the first block. Oh, you can't see that. First block, and the kinetic energy of the second block. Okay, so that's going to be 1/2 mv squared, right? mv squared, okay, plus 1/2 m. Now our v here is in the opposite direction, so I would put minus v here, squared. Of course, a minus sign squared is just a plus sign, right? So it doesn't really matter that I have that in there, but just for the sake of understanding, we would put that in there, okay? Now, so we have 1/2 mv squared plus 1/2 mv squared. That gives us mv squared here. Okay? All right, so that's all about inelastic collisions in one dimension.